So this is for the stumper problems. And let's first look at when you can use this. So if and only if you try the initial substitution and get either 0 over 0 or infinity over infinity, you can most likely use L'Hopital's rule to get the limit. There's one very important thing: never use this if you have a number, a non-zero number over 0, or anything except 0 over 0 or infinity over infinity. And L'Hopital's rule is very simple and very powerful. And there's the temptation to use it all the time. Do not succumb. You can only use it in these circumstances. Basically, only use it if everything else has failed. So, this is a rule. The limit as x approaches a of f of x over g of x. So if we were looking at something like here, where we've got x is approaching some number, we've got some function over some other function, it turns out that that is the same as if you take the limit as x approaches a of the derivative of the top divided by the derivative of the bottom function. Note, this is not the quotient rule. It is not f prime g minus fg prime over g squared. It is not really parallel to anything else we've seen before. It's its own separate thing. What this means you take the derivative of the numerator over the derivative of the denominator, then find the limit again, the answer is the same as the original limit you were looking for. If you get 0 over 0 or infinity over infinity again, you can repeat the process. So, let's say we're trying to find the limit as x approaches 0 of the sine of x over x. Well, if I try it with my substitution first, this tells me that there is a removable discontinuity. It's the indeterminate form, it's called. But I can't factor that. Sine x, those don't factor. So I can't use my original technique. And because it's 0 over 0, I can use L'Hopital's rule. So what I'm going to do is I'm just going to say that this is the same as the limit as x approaches 0 of the derivative of sine of x over the derivative of x. So the derivative of sine of x is cosine of x. The derivative of x is 1. And now, whoops, I should have a limit still written in there. And now when I substitute that in, cosine of 0 over 1 is 1 over 1 is 1. And there's my limit. This can normally be done with the squeeze theorem, but L'Hopital's rule works beautifully for it. I can do this. This is the same as one we were doing earlier with factoring. When I plug that 3 in, I get 3 squared minus 9 over 3 minus 3, or 0 over 0. So yes, I can use L'Hopital's rule if I want. I can also factor. We did that one earlier. But we're practicing the rules, so we're going to take the derivative of the top over the derivative of the bottom. I always want to forget to write that limit. Bad Ms. M. Bad Ms. M. Limit as x approaches 3, so take the derivative of that top one, that's 2x. Derivative of the bottom is 1. And now when I substitute that 3 in, there we go. Same thing as we would have gotten the other way. We can also do much funkier problems. This one would typically be done with what's called rationalizing the numerator. You might hear that and think it's a little funky because didn't we rationalize the denominator in pre-calc? And yes, we did. This is a related technique, but something a little bit different. Basically what happens with this one is if we put that 2 in, we see that it is indeed a situation where we get 0 over 0. 2 minus 1 is 1. Square root of 1 is 1. 1 minus 1 is 0. And basically the problem with this is that it's kind of been over-factored. We would basically be wanting to go back a step, multiply by the numerator, except with the sign reversed, in order to make this turn into something that doesn't equal 0 over 0. It's sort of not quite the opposite of factoring, but it's kind of like it's been factored too far, and we will want to undo that. But this technique takes a lot of time, and it has a lot of places for things to go wrong, and it could really be done just as easily by taking the derivative. So remember that this is to the 1/2 power. We're going to do the derivative of x minus 1 to the 1/2 minus 1 over the derivative of x minus 2. So we'll bring that down, 1/2 x minus 1 to the negative 1/2 times the derivative of x minus 1. Derivative of negative 1 is 0. Derivative of x minus 2 is 1. So this is 1 over 2 square root x minus 1. Derivative of x minus 1 is 1. This is all over 1. So now we can just substitute that in. 1 over 2 square root of 2 minus 1. 2 minus 1 is 1. Square root of 1 is 1. 1/2. And L'Hopital's rule can also be used when we're working with infinities. So limit as x approaches infinity. These were the problems in limits 3. So let's say we have x over e to the x, and we're trying to find the limit. And it's really not clear in this. it's really not clear which of these is a bigger infinity in a sense, although it is e to the x, incidentally. But these don't really cancel neatly. There's really no good way to simplify them like we were doing. We can't say behaves like, because we've already narrowed it down to one term per numerator and per denominator, and we still don't know what to do with it. And so this is a situation where L'Hopital's rule is really, 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 really useful. Because what's happening here is that this is going to be an infinitely large number, and this is going to be an infinitely large number. And so we kind of think of it as that indeterminate form, infinity over infinity. We can't really substitute in infinity, but think of it infinity over infinity. And if we have that, that means that we can use L'Hopital's rule again. If it was 1 over a really large number, or if it was a really large number over 10 or whatever, no dice. It's only when it's really large over really large. This is why I taught you the other way of doing things in Limits 3, simply because for the problems that we were working with, this, for example, or oops, that's the wrong page. These wouldn't necessarily be ones that you would do more easily using L'Hopital's rule, because they're pretty straightforward to do as long as you have the pattern down. This one, however, is not easy to do. So let's turn that into the limit as x approaches infinity of the derivative of x over the derivative of e to the x. Derivative of x is 1, derivative of e to the x is e to the x. And now we're looking at, as this gets very, 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 very large, what we have is we have a positive number over a large positive. Positive divided by a positive is a positive. Any number divided by a very, very large number is going to get closer and closer and closer to 0.